So to continue in section 4.2, the other day we introduced E. And the important thing about E is to realize it's a nice natural constant, 2.7182818, etc. Now, the digits of E are kind of like the digits of pi. They never end and they never repeat. I don't know what the record is for memorizing digits of E, but the record for memorizing digits of pi is around 70,000. Which is a staggering amount of digits to remember because they're all random. But E is the basis of our exponential function, and we can use our exponential function to calculate continuously compounded interest. So let's do a little bit of practice of that. The formula for continuously compounded interest is A equals P E to the RT. Now, I will give you this formula on an exam, but you have to know it, you know how to use it, and know when to use it. Because this is for continuously compounded interest. And then there's another one which I just call simple interest. And actually the formula for that one's a bit more of a pain. That's when you have interest compounded every so often. N times a year they're going to give you interest on your account. N could be 2, that'd be semi-annually, 4 quarterly, 12 monthly, or 360, which perversely is daily. So, in any case, let's practice with problem number 34. We want to invest $3,500 in an account with continuously compounded interest, getting 6.25% interest per year. For part A is 3 years. And the question is, how much are we going to get back when we do that? Well, first of all, good luck trying to find something that's going to give you 6.25% interest right now. Interest rates are really, really flat. But beyond that, let's just look at the math here. There is one more important thing about the interest rate we should take note of. It's as a percentage right now. We need to write it as a decimal. So what would 6.25% be as a decimal? Thank you, 0.0625. So it makes a world of difference what you put in your formula. If you put in 6.25, you're effectively telling your formula that you're getting 625% interest. If you have a place where you can get 625% interest, please share it with your instructor. I'll give you an A. All right? But 625%, that's even beyond loan shark standards, I would think. What's that look like when we fill everything in? Well, we're going to use this formula. A is our unknown, 3,500 E to the 0.0625 times 3. So take out your calculators. So I want 3,500. Where are you going to find e to the x? Does anyone remember? Second ln. And then we want 0.0625 times 3. Now, if when you do the second ln, it gives you something like this, 3,500 e caret. If it doesn't give you a nice exponent, then what you're going to need to do is type a left parenthesis 0.0625 times 3. So if you get that caret, then you need to use parentheses. If you don't, good, your operating system's up to date. You should just be able to press enter at this point. I would point out that I expect for interest problems that you round it to the nearest hundredth. Why the nearest hundredth? Yeah, it's pennies. All right, we don't have any currency that goes below pennies. So this would be approximately $4,221.81. If you forgot this, if you forgot to change that to a decimal and just typed in 6.25, it probably will overflow your calculator. I'm not sure, but we'll take a look here. Maybe not. We'll see. All right. So what if you forgot to put in that decimal? or change it to a decimal. Well, then that's telling you you got this number. What is this number? Does anyone know? What's this E11 stuff here? Yeah, so really what you're saying is you got 4.86 times 10 to the 11th power dollars. So let's figure out what that means then. So it's going to be 486, and then I need 9 more decimal places. So basically, your $3,500 turned into $486 billion. All right. So hopefully, if you saw that, you might go, well, I'm not so sure that looks right. All right. Hopefully, engage in a little critical thinking there, because, man, if I could do that, I would have been retired a long time ago. Okay. Do you need to practice another one with continuously compounded interest? I mean, that's an absolute, pretty much lock for an exam. So are you good with continuously compounded interest? Let's try problem number 24. Kind of another use of these things. Radioactive decay. And let me give you an example just to help you get started with radioactive decay. Has anyone ever heard of carbon-14 dating? Yeah. Okay. It's a way they use to figure out how old certain organic objects are. So as long as it was living, breathing at some point in its history, then you can do this. So let's figure out if you have 100 grams, this isn't problem 24 yet, 100 grams of carbon-14 in an initial sample. How much is left after 5,730 years? Well, you need to know a formula that I will give you, or at least give you enough information to derive. A equals A sub 0 e to the negative 0.000121 times t. So A sub 0, that's your initial amount. That's how much you start out with. T, of course, would be time, and A is your final amount. So really, I'm giving you kind of a fancy way to put in something into this formula. What numbers have I given you here? What's the 100 grams going to represent for us? That's our A sub 0. All right, so that's A sub 0. And obviously the 5,730 is time. So overall, it should look like this. Our final amount is 100 times e to the negative 0.000121 times 5,730. Now what I want you to do is I want you to calculate this on your calculator before I do, and kind of round off your result. It should round to something kind of interesting and suggestive about the problem and the nature of carbon-14 dating. And again, if you get that character up here, how many of you are getting a little character when you hit the E to the key? All right. So if you got an 83, then you're out of luck. But if you got a 84, you can update your operating system. And I kind of encourage that. All right. But if you got, all you have to do is use a parenthesis. So you don't need to, let's say, go buy a new calculator. 100 second ln negative. Make sure you use the negative on the bottom row of your calculator, not the subtraction key. 0.000121 times 5,730. All right, so before I hit the enter key, what did you guys get? About 50, right? Now, how does 50 compare to what you started out with? Michael? How would you compare 50 to what we started out with? Someone help out? Matt? Yeah, it's half. All right, you start out with 100, you have 50, it's half. So it's half of what you start out with. So what they say then is 5,730 is the half-life of carbon-14. So all your radioactive isotopes are going to have a half-life. And it's how long it takes, on average, to roughly decay to half of what you started out with. Now, carbon-14 is 5,730. Lead has a half-life in the billions. Uranium, strontium, lead. I think lead is the result of decaying of uranium. But I think the lead. There's something that's, I don't know. I'll have to double check. Lead should be the end. I thought I heard somebody saying something about lead. All right, let's skip lead. Let's try strontium. Strontium, cesium. They all have half-lives. So we get about 50 grams. So let's take a look at problem 24 then. Problem 24, they give you the formula and they ask you a couple questions. So 24, m of t equals 13 e to the negative 0.015 t. And they asked us for two things. They asked us to find the mass at time 0 and the mass after 45 days. So how do you think we're going to find the mass at time 0? Yeah, so part A is plug in 0 for t. Now, you shouldn't need your calculator for this one. Yeah, what you're going to get is 13 times e to the 0, which is 13 times 1, or 13. One thing that I'd like you to see out of this is why I called this a sub 0, or the beginning amount in our previous example. And that is because when you put in a 0, this term's going to go to 0, or this term's going to go to 1. You'll end up with that as your beginning amount. So 13 is the initial amount. How much is left after 45 days? About 7. Okay. Thank you. So 13 e to the negative 0.015 times 45. All right. So on an exam, I'll tell you where to round it. I mean, if you're rounding to the nearest digit, then it's about 13. Or about 7, sorry.
Did the formula specify that it was in days?
Yes. Yeah. So it's the formula mentions that it's in days, after t days. Yeah, otherwise you'd have to convert to whatever unit is expecting t to be in. So, good question. Let's do a couple more applications of exponential growth. And we'll work with world population growth. Now, the thing about populations is that they tend to grow exponentially. So, for example, does anyone know how many people are in the world currently? Yeah, 7 billion, about 7.4 billion, which I looked up the other day, and I was stunned because it's about 4 years ago that we had 7 billion. So we've added 400 million people to the world in the last 4 years. Wow, it's a crazy amount of people. In any case, so I don't know the annual growth rate. Actually, we could probably figure that out. But let's just use about 1.9%, which was a relatively high growth rate that the world experienced back in, I think, the 60s or 70s. Let's project what the population is going to be like, moving into the future. How's it going to grow? What's it going to be? So how far in the future do you want to look? How far in the future do you have the courage to look?
50 years.
50 years? All right. So about the time you're into your retirement, right? 50 years from now. So let's put in a 50. Any predictions before you calculate it out?
High number.
Pretty big. Now keep in mind that this is going to be the units in billions of people. I'm thinking that's going to about double. Wow. Well, it's a good question, and that'll lead us into a different problem. I think problem number 29 is a good follow-up to this one. So this assumes unconstrained growth, meaning that we can just keep on adding more and more people, but that might not be realistic. What'd you get? 19.13 billion. Now, I'm sure a lot of people would argue, well, wait a minute, that's not realistic because, at some point, you're going to run out of food. There's only so much arable land. There's only so much food that we can produce, energy we have. You're just going to run out of room. So what you can use is a model that kind of assumes that, well, at some point we got to level off. There's only so many people that an environment can hold. So let's look at problem number 29. And it gives you what's called a logistic model. And that is P of T is 73.2 divided by 6.1 plus thank you. Thank you squared. Okay. 5.9 e to the negative, I need a little more light here, 0.02 t. E to the negative 0.02 t. So this is, like I said, kind of a constrained model. And I think this is assuming that there's a limit. Well, I know this is assuming that there's a limit on the growth of the human population here. So I'll tell you what, let me do this real quick. Let's take a look at this graphically and see if that looks a little different or makes a little bit more sense as opposed to our previous one. So y equals 73.2 divided by 6.1 plus 5.9 e to the negative 0.02x. Okay, so I think we're going to have to zoom out a little ways. And all right, doesn't look like it's growing uncontrollably. Let me see if I can adjust the window a little bit. On the x-axis, we'll go from 0 to, say, 100. And on the y-axis, we'll go from 0 to 13. 13. Okay. So the population starts out around 6.1, but then it levels off. And you can kind of see the shape of this function. So where does it level off? Well, that's a good question. Let's see if we can't figure out a couple things here. It says, what does the model predict for the population for the year 2200? Well, let's see. What do they consider to be year 0? Year 0 is the year 2000. So if I want year 2200, that means t equals 100. So let's put in 100 into our model and see what we get. as you do this on your calculator, make sure that you're careful with the parentheses if you're using them. So 73.2 divided by left parenthesis 6.1 plus 5.9 e negative 0.02 x actually times 100. I guess I should get rid of the x. And then a right parenthesis. It's about 10.6. And that would be in billions again. Is everyone able to get 10.6 off their calculator? Good question. T equals 0 was year 2000. That's what the problem gave you. You know what? This should have been 200, shouldn't it? All right. Well, there's a cool thing, and actually I was going to show that anyways. So in this case, I showed it out of mistake, but I was going to go back and do it anyways. If you hit the second key, then the enter key, it should bring up your previous calculation. And all we need to do is go back here to the 100 and change that to a 200. So go back there using the arrow key, edit it. Now we got 11.79 billion people. So yeah, great question. Thank you. But that's a nice trick. If you've made a mistake or you just need to repeat the calculation for a similar value. So 11.79. And that kind of goes along with what we were seeing from our graph, is that things are going to level off. So if you do 2,300, that means t equals 300. I doubt we're going to get much higher, much closer to 12. 12 is going to be the limit, at least according to this model. Yeah, so we get 11.97. So not a huge difference. So you really kind of leveled off when you get out that far along the x-axis. Are you comfortable with our calculations with E? Because that's pretty much what this whole section is about. It's just various calculations with E. I'll do one more or not, it's up to you. No clamor for one, so for homework, try 7 through 15, 23 through 29, 33, and 35.